Welcome everybody to OpenCV weekly webinar. And today we have with us Team CEREBROS. It's a team from Egypt that has won the third place at OpenCV AI contest last year. And it is a team of undergrads. There were 10 people in the team, 3 of which are with us today. And right after I introduce Phil, we will go back and have a detailed introduction from each team member. But the important thing to note is that they have gone through several difficulties to win this prize. And you know, the device itself was stuck in customs for a long time, but they pushed through, and it's a real pleasure that they were able to bring such a good solution. So welcome, Team CEREBROS.
Thank you, Satya, for this quite good introduction. As Satya said, we are CEREBROS team. We are a group of undergraduates, and we proudly was one of the participants in OpenCV AI Competition 2021. And we got the first place for MENA region and third place for the global region. And I'd like to introduce my friends, which they helped me a lot, and they were the pillars of the team in conducting this quite awesome project. My friend Abdurrahman, who will talk about the embedded systems and the system structure of our project, and my friend Muhammad Ahmed Salah, who will give us the sum up about the project and the importance of the project itself. So I'd like to start sharing my screen.
1 second, I just wanted to introduce Phil also for people who are new to OpenCV weekly webinar. Phil is our content manager, and he is responsible for putting together the webinar. If anything goes wrong, it is basically Phil's problem.
That's just good advice for life. It usually is my fault somewhere down the line. Thanks for that introduction, Satya. If this is your first time, welcome. Thanks for joining us. There's a couple of things we do here every week, one of which is take questions from you in the audience. So please use the Zoom Q&A button to ask your question at any time during the webinar for you in the Zoom audience, and we'll do our best to answer as many as we can at the end of the episode. We'll also be doing a giveaway of $200 worth of Microsoft Azure credits from our sponsors, the sponsors of OpenCV AI Competition 2021 and OpenCV AI Contest, which you should check out. We currently have submissions open for that right now on the OpenCV website. You'll be winning that if you answer the trivia question, which I'll ask at the end of the webinar here. So stay tuned for that.
That's great.
Okay, I will share my screen right now.
Yeah. So I want the audience to remember that this is a team of undergrads, and they did this project for their final year, class project, which is important for graduation. So a lot was accomplished by a relatively small team in a very short period of time, and they went through a lot of trouble to get this, the devices, etc. So kudos to them. Let's get started.
I'd like to start with spotting the light on the problem we tried to solve at the beginning, which is the problem of completely paralyzed people. We tried to make a proof of concept for a wheelchair that performed the task of collecting the brain signals and use those brain signals into controlling the wheelchair and giving the wheelchair the right command for movement. And as we see, according to statistics, there are many individuals in the world that suffer from complete paralysis. So we try to use a combination of the technologies that's on the scene and the technologies that we aim to learn in solving this problem. And I will take you through the main components of our system. Firstly, we have the brain-computer interface, which is the system that is responsible for exciting the brain signals and collecting the brain data to convert it to a control command, and the classification model that is used to classify these signals into directions so that wheelchair could use for movement. Second, we have the control module, which is the system or where we start to integrate many of submodules like computer vision and brain-computer interface, and also the safety sensors into our wheelchair. And lastly, our application, which is aimed for the caregivers to be able to monitor the patient while using the wheelchair. For the PCI, we actually tried to use many headsets and to compare each performance of each headset. The headsets are the EEG sensors that is responsible for collecting the brain signals, and we used those headsets in controlling the wheelchair. So the comparison was made on the price of each headset, the accuracy of the data collected, and the noise cancellation in each board or each device, and also the comfort of using these headsets. As we know, it aimed to be for patients that has a very quite rough medical condition. So we decided to make a proof of concept, but to put into considerations the comfort of the users. After that, we made our own dataset to train the model for the controlling the wheelchair. For each headset, we used different methods for data excitation and data extraction, and also the model used for each headset was different. And the reason why we used two headsets, first, we tried to make a basic proof of concept using only a NeuroSky headset, which is a one-channel headset, and the only channel for the headset was placed in the frontal cortex. So the only source of the data was the frontal cortex of the patient. And after that, we tried to upgrade our project to give a better accuracy and also a better functionality. So we decided to use the site on board, which is an 8-channel headset. And we used those channels in different areas in the patient scalp. And we mainly concentrate on the motor cortex, which is responsible for imagining the movement of any organ, like hands and legs. So we try to use this headset to make a better accuracy for our model and to make a good functionality. After that, we tried to collect our dataset, as I said, and we got a lot of volunteers that they helped us a lot in making our dataset to make a better model for controlling.
So one question I have, Nurhan, is what does the data look like? I mean, I have actually never worked with this sort of data. So what do you tell them, like when during the data collection process? I mean,
yes.
I'm think about me as a novice who doesn't know anything, right? So you're putting these headsets on people. Are you asking them to imagine something? I mean, forgive me if
Yes.
I'm just asking stupid questions, but I really don't know much about this.
No, actually, it's not a stupid question. If I were a new human that see this for the first time, I will ask how they think or what is the process that makes the brain signals specify this is the right direction or the left direction. So for each headset, we tried a different method of excitation. For site on board, we tell the volunteers to think if they moving their right hand up while they just thinking or imagining that they move their hand up, and the premotor cortex induce or conduct a signal, a pattern that we take these signals and classify them to the right direction. And we made the same procedure for the left and the forward and backward directions. So
Got it.
it's all
And
about imagining the movement of the limbs and hands.
okay, and the output you get, so you ask them, okay, think about as if you're lifting your hand, and the output is a vector of numbers. What does the output look like?
Yes,
A time
it's
series?
pretty much like
Yeah.
a time series, and this time series has a frequency of about milliseconds or even smaller. So
Right.
it's a vector of raw EEG data, like a time series, but with a smaller frequency.
Interesting. So it's a vector of numbers, and with some frequency, you get this output.
Yes.
And is this vector interpretable? Like what does this vector represent? Can you interpret it, or you just take it as, okay, it's some data coming out of the EEG machine?
Okay, each sensor had its own translation for these signals. It's just an electromagnetic signals that is collected by a device. So each so each device we use have its own interpretation to these signals, and using the supported equation they give with each headset, we able to convert this vector of data into signals in millivolts. So it's distinguished using these supported equations.
Got it. Got it. Got it. Yeah, that's exciting. Please go on.
Okay. After that, we managed to make our custom model using convolution neural network, and we have tried several architectures to use in classifying these data, but convolution neural networks works best for us because each record we supported with the model is relatively huge in size. So the convolution neural network help us in processing these data in terms of accuracy and also the speed of processing. We found out that when we deploy the convolution neural network models that work best for us on the microcomputer we used in our device, it was the fastest in response. So we stick with the convolution neural network model. But also there were many successful models, but convolution neural network was the best one. After we found out the best architecture for us, we faced two main problems, which is the smoothness of the movement wasn't actually as required. As we see in this video, the patients think about the direction that he wants to move in, but the size of the buffers that we collect the data was relatively taking the time in order to process this data. So we tried to optimize the extraction process and the feeding for the data to the model to make the size of the buffers that we feed to the model a little bit smaller. After we managed to optimize our model, the smoothness of the movement were as much as that is required for the patient. And we stick to that pre-processing and that processes that we made on the data that makes the model response fast to the user comment. And for safety, it was the only thing that helped the problem of the collision for the wheelchair. Sometimes it was for the wheelchair to know what is surrounded. So the computer vision played a huge role here using OCD cameras, and we deployed mobile net SSD model on the OCD camera. It was able to detect the targeted object like humans and vehicles in the street, and also some kind of animals like cats and dogs, etc. And using computer vision and the distinguishing between the background and those objects made in an extra safety layer for the wheelchair, where the computer vision had the control to assure for the wheelchair if it's safe to conduct the processing about the brain signals data on the wheelchair. as if the wheelchair or the computer vision saw that there is an obstacle or any human passing by, the wheelchair will stop immediately and neglect any comment or any movement comment that is came from the headset.
Right. So basically it is assisting because, assisting the people based on visual information, because they may not be even looking at, there could be a car coming from the side, which they completely missed,
Yes.
but they want to still cross the road. So
Yes,
computer vision
absolutely.
will assist them in overriding that, okay, it is not safe to do right now, we'll wait.
Yes. Yes, basically that's right. And we used the cameras in many directions to support this aim, as many of these patients aren't even able to move their heads. So the computer vision play a huge and vital role in doing that.
And how many cameras did you use in the application?
We use mainly 3 cameras, but we wanted to use 4 cameras for each direction, but we found out that 3 cameras are enough for the proof of concept, and it works perfectly as we want.
Right. And what about the speed of this system? At what, I know that wheelchairs do not need to be fast, but
Yeah.
how fast were you able to process? So there are 2 kinds of processing, right? The EEG data processing, as well as the visual data processing. Is that about real time?
Yes, and I will let my friend Abdurrahman, who is responsible for the hardware system, talk about this perfectly rather than me. But yes, we put into consideration the speed of the wheelchair must be as a standard, about 1 meter per second or something quite like that. But my friend Abdurrahman will discuss this in a perfect way.
In our control system, in movement, we have 3 ECUs. One of them is responsible only for movement. We take the command from Raspberry Pi that receives the command from PCI or joystick that for caregivers or hospitals. We not put the speed directly on DC motors. No, but we check on the safety ECU if the wheelchair is stable, or and if the cameras take all readings as well. Then we put this command forward it to the movement ECU. This movement ECU accelerate the PWM signal to the target speed, not put it directly. And we also made the deceleration to make the DC motors may move smoothly, not put it directly on the DC motors. That make our system more smooth.
Right.
Is it clear?
Yeah. Yeah.
Okay. We also use the locating the process in the computer vision for each object detected to convert the 3D coordinate of each location for these objects surrounded to the wheelchair. We wanted to convert them into GPS coordinates, longitude and latitude, in order for us to translate the environment around the wheelchair into map. So any caregiver could see what is happening around the wheelchair user and see what if a passerby or a car passing by the wheelchair remotely, of course, and this will alert the caregiver if anything happen or if the wheelchair collide with a car or a wall or anything of this stuff. And also, the mobile application have a lot of features that my friend Abdurrahman will talk about later for safety monitoring the patient and the wheelchair. And I'd like to say that the safety of the wheelchair wasn't only if wasn't already depend on the computer vision only. We use the brain-computer interface also to detect the awakened state of each patient, as there must some of these conditions or health conditions for the patient make them feeling sleepy without, say, realizing that they are drowsy or they will fall asleep. So we made a drowsiness detection model using also the brain-computer interface to detect whether the patient is awakened and it's okay to take the command control that is taken from the brain signals and conduct it. And whether the patient is feeling sleepy and they feel light, and in this case, the wheelchair must stop immediately. So we tried many systems for safety action. And here is a proof of concept about safety. We used the GTA game in order to control this car using brain signals. If the patient is drowsy, the car will stop, or if he is awakened, the car will still moving. And after that, our friend Abdurrahman will talk about the system in detail. So I will let him come here.
Now I will talk about the control and safety system for our wheelchair. We have two modes for control system, PCI mode and joystick mode. Joystick mode that for caregivers and hospitals. PCI mode that for the patient only. Our microcomputer board, Raspberry Pi, the heart of our system, receives the command from PCI or joystick, then forward it to the movement ECU through campus after checking the readings from safety ECU that interfaces with IMU sensor and ultrasonic sensor to check wheelchair orientation and status. That's for control, and also speed. We talk about it later, that we use acceleration and deceleration to make our wheelchair move smooth. Then the last issue that I will talk about is the battery indication ECU. This battery indication ECU that monitor the battery level and battery charging. Yes. After that, I will talk about our feedback system that takes all these readings from medical sensors that monitor patient status, and also safety sensors for wheelchair, and send it through topics to MQTT server. Then the IoT application subscribe from these topics and view it on our mobile application. Then we'll show about a small demo about our IoT application. Yes, that's it. It's this marker indicates the wheelchair location. It takes the relative coordinates from GPS and the OKD cameras to appear this location on Google Maps. It's also, after that, there is another tabs in our demo that monitor patient status and also monitor our body temperature, ambient temperature, battery state, and also wheelchair state. It's all about our mobile application. Then we'll talk about our hardware system.
I have a question about the messaging. I don't. Is everybody in the crowd familiar with MQTT? Because this competition was the first time I'd ever really seen it, being used for robust apps like this. Could you briefly maybe describe how MQTT functions?
How MQTT functions? The MQTT functions. it's take the readings from topics like speed topic or IMU topic. It takes it from our client is Raspberry Pi, sends it to MQTT server. Then the IoT application subscribe from these topics and make it visual on IoT application. Is that clear? Or
Yeah, I'm wondering more like what are like the benefits of it versus, because there's so many different ways to send messages with these sort of apps. So what makes MQTT so good specifically for these sort of embedded uses?
this this part is we have another colleague called Amr Zaki that can't attend this day. He chose this MQTT server and know more about it. It's not my part.
Yes, I will take this. We decided to use MQTT because it's relatively used with IoT devices. So we used the server Chipped.io as a server for us in order to publish the messages for the biological sensors and also for the battery state and the OBJ cameras coordinates for each object detected, and then publish this in order for the server to have this data in real time and then feed this data to the mobile application to be also dynamically available for the mobile application we made.
Thanks. That makes, I mean, that definitely helped.
Okay, Abdurrahman, you can continue from here.
Oh, okay.
To system design.
We designed our PCB boards. Our system consists of three PCB boards: top board and bottom board and indication board. For top boards that consists of Raspberry Pi and ECU that interfaces with the medical sensors, heart rate and temperature sensors. We also bottom board consists of two subsystems. That are first subsystem, another microcontrollers that interface with motor drivers and safety sensors like IMU sensor and ultrasonic sensor. The second subsystem that our main board distribution board that takes voltage from battery, then distribute all these volts to ECUs and sensors and make a stable powerful OKD cameras. Then we fabricate all these PCB boards in Egyptian manufacturers and assemble it using their tools because we have sensitive SMD tools, so we fabricate in the factories. That's about our hardware fabrication.
It's pretty cool. I love watching the surface mount videos. Are very satisfying.
And lastly, we hopefully wanted to explain our project in a quick explanation, and we are ready to have questions.
Could we, you know, it might help if we watched your final submission video. We usually do that with the teams from OpenCV AI Competition.
Yes,
could
of
we
course.
share that on like YouTube, or if you have it locally or something?
Yes, yes, of course, and I can share it right now.
Yeah.
Okay.
Awesome.
Wait a second.
Well, you're getting that ready. Actually, yeah, Satya, check your Slack messages. I think I figured out how to get the LinkedIn streaming if you want to do that for Q&A here. Lots of good questions here. Keep in mind, folks, we'll be doing Q&A shortly. So please use the Zoom Q&A function. We've got a ton here. Thanks for sending those in. We'll also be doing our giveaway right before we do Q&A here. So I have one question, which is, I always like to ask this of everybody. What surprised you most about building this during the competition?
I think what surprised us the most is how the technological development there here real time could help us in making such a project and using such a product like OBD cameras, which is, I think, an industrial product, and it works very, very much perfectly with our project, and the processing on the camera was in real time, and that is the most thing that was exciting to me as Anorhan. And I think we learned a lot in this process. We learned a lot of a lot about new technologies, and we had faced a lot of models that were open sourced, and we used these models for computer vision and for even learning more about computer vision. So that was a very splendid journey.
Yeah, go ahead and hit play on the video. Do we have audio on this?
Yes, okay. Yes, we have on.
You might need to reshare your screen. There's a little button you got to check to share audio when you share the screen on Zoom. It's annoying,
Okay,
but necessary. It's a little checkbox in the bottom left corner. It will say shared audio.
okay.
Machine learning.
Yep, that worked.
Yep, that worked. Thanks. Hi, we are CEREBROS, a group of technology enthusiast engineers representing Alexandria University in Egypt. We have practical experience in several areas, including embedded systems, robotics, and machine learning. We decided to apply this experience in solving one of the problems facing the medical field. Technological developments in the area of brain-machine interface, known as BMI, have received our attention. The motivation for our choice to apply brain control technology to wheelchairs has several reasons. Firstly, the large number of patients who cannot control their wheelchairs by themselves. Amyotrophic lateral sclerosis, brainstem stroke, brain or spinal cord injury, cerebral palsy, muscular dystrophies, multiple sclerosis, and numerous other diseases impair the neural pathways that control muscles or impair the muscles themselves. They affect nearly 2 million people in the United States and 10,000 children every year in Egypt. Secondly, the wide market for wheelchairs and annual market growth rate of wheelchairs, which is 7.6% from 2015 to 2026. Our strategy to add a new feature to these chairs is to enable patients who are completely unable to move to control the chairs through brain signals and enable them to regain some mobility safely and easily indoors, as in home, healthcare, and hospitals. And to move outdoors as well, such as in the streets or any open area with minimal infrastructure modifications. Our brain-computer interface makes use of EEG, which is an affordable, accessible, and non-invasive technique to detect brain activity. For multiple channels headset, motor imagery signals are used to operate the wheelchair by detecting a suppression of the 7 to 13 Hz in the sensory motor cortex, which is the brain area associated with movement when users imagine movements. After successfully being able to control the wheelchair, deploying our own build from scratch deep learning model based on a convolutional neural network, we had to add many safety and monitoring features to the wheelchair in terms of knowing the surrounding environment and avoiding collision. The most common technique used by automotive companies is using short-range sensors like ultrasonic and IMU to detect the stability of the chair, and also a battery management system to check whether the battery needs to be recharged or not. And both of these features can be monitored from the mobile application by the caregiver responsible for the patient. And
But
also
short-range
battery
sensors
management
have a lot of
system to
drawbacks
check
and
whether
are
the
not
battery
reliable
needs to be
enough to
recharged
guarantee
or
the
not.
complete safety
And
of the
also a
patient.
battery.
I
So we
think
decided to use computer vision in autopilot application using OpenCV. To control the chair, there is a lot of digital signal processing processes and millions of mathematical equations being calculated in real time for the machine learning model. And all of that needed a huge computational power. So adding more models for the vision will cost more computational power and may cause a delay in the performance. The OpenCV camera from OpenCV is a perfect solution for this problem, as it has an onboard processor, which is the Movidius Myriad X visual processing unit, that can perform up to 4 trillion operations per second, which is faster for computer vision and AI tasks. 3 OpenCV cameras are used in left, right, and front of the wheelchair to detect any moving vehicle and pedestrians. Then locates each object by calculating the distance and angle between the wheelchair and all of the targeted detected objects. Or if it needs to stop. We also use the camera stream in mapping a localization by determining the coordinates of the wheelchair and putting all surrounding vehicles in Google Maps with a simple technique. When starting the wheelchair, we first get its longitude and latitude coordinates using a GPS measured in degrees. So we calculate the distance. We wouldn't have finished our project in that great way if it wasn't for our great sponsors. Thanks to them and thanks to OpenCV for their technical support and the offered courses.
so. That is our video submissions that we submitted.
Thanks. Yeah, and it was good enough for first place regionally and then third place overall for sure.
Thank you.
Congratulations.
Yes, so let's we can do our trivia question real quick here before we go switch over to Q&A. Thanks again for the presentation. This is the first time that we're actually on time on the show in like months, and so I don't know what to do now. So if you've never joined us before, the way this works is I'm going to ask a trivia question based on the presentation that we just watched. If you answer that question correctly in the little Zoom chat window here, the first person that answers it correctly will win $200 worth of Microsoft Azure credits from our sponsors at Microsoft Azure. So get ready to answer the question in the chat window there. Like I said, first person to get it right wins. So they mentioned the brain-computer interface works in a specific range of hertz. What is that hertz range?
Yes, it works for.
Hold on.
That's the
That's the trivia
audience
question.
questions.
Yeah. Sorry.
It's okay. Nobody's gotten it yet. You're close. It's a range. Some of you have the first one right, but not the last one. Ooh. Close. Oh, I finally stumped him, Satya. Oh, man, nobody's gotten it yet. Ooh, everyone's just guessing random numbers now. I think I finally won. I beat the final boss of OpenCV weekly webinar here. We might have to call it and pick the closest one.
Why don't you pick the closest one and then let them iterate on to refine it?
Yeah, the closest. So some of them have gotten it right. I'll give you the bottom end is 7. The bottom end is 7 hertz. What is that? What is the full range? 7 to what? There we go. Louis Pierre Morin gets 7 to 13, which is the correct answer there. Thank you. Please send me one email to phil@opencv.org, and we will make sure you get your Azure credits. Congratulations. Yeah. So lots of questions on this episode. I'm going to start with a question from Zach, who would like to know, did you explore any like predictive path logic? Did you consider maybe trying to guess what the operator's intent was if, say, for example, the device sees a sidewalk nearby and the BCI says they're trying to move sort of towards the sidewalk, would you just maybe guess let them say that, yes, just take me all the way to the sidewalk?
I think this type of prediction needs another type of processing, which needing time series forecasting or some sort of these pulses. We didn't made it yet, but it's quite impressive idea. I guess I have thought about it actually, but we didn't made it yet.
Yeah, it's interesting. I mean, you have to be really careful about those sort of things because you don't want to. Guessing wrong is pretty bad in those
Yes,
situations. Taking someone somewhere they don't want to go is basically a worst case scenario with these kinds of assistive
but
devices.
I think that's why we used the computer vision, because if there is anything that is passing by or any obstacle, and also we use IMU and ultrasonic. If the ultrasonic detected that there is a sidewalk, it will immediately stop and neglect the comments that is given by the human and the user print signals.
This makes sense. Partho would like to know, how exactly were the cameras mounted on the wheelchair, the OAKDs?
Yes, we tried to make some kind of pillars to hold the cameras to be quite fixed and to be able to see the view in the right view that we wanted to. And our mechanical team, or our mechanical small sub team, had designed these fixtures, and they managed to make it in the good place.
Excellent. DK would like to know about the kind of battery that you ended up needing to use. What sort of power did the cameras and the Raspberry Pi and all that end up consuming?
I think Abdurrahman will answer about this question very accurately more than me.
Okay, we used the 24 volt battery that comes with the wheelchair. It's a lead acid battery which provide voltage and the current rate is really impressive to support all these powers and the current consumes dedicatedly for DC motors that consumes more current other than the other sensors and the STMs, ECUs, and the Raspberry Pi. It supports the more sufficient power for us. We also support a stable voltage for OKD cameras. We use buck converters that step down voltages and make it stable for OKD cameras.
Yeah, I mean, I hadn't. This is one of the solutions in the competition that had, multiple devices. There weren't a lot of them that used more than two, really. And a couple of the winners, Topspin Trackers was another one that used a couple, memory serves. But there weren't a lot of them, and it does, even though it's a very low power device, I expected it to need more for three of them.
Yeah.
It's surprising how low the power use was, even with three of these plugged in, and it'd be even less, I suspect, with OAKD Lite. Anton would like to know about the performance of the EEG CNN on Raspberry Pi. What model of Pi were you all using for this again?
The Raspberry Pi 3. We used two models of Raspberry Pi. The first was Raspberry Pi 3, and after using the OAKD cameras, we wanted to upgrade to Raspberry Pi 4 for a better performance.
What kind of performance increase did you see in terms of the processing time on the 3 versus the 4?
Okay, I think the reason why we moved to Raspberry Pi 4 was because the board itself, the microcomputer, was getting so hot. So we wanted to manage this power consumption and upgrade for Raspberry Pi 4. But actually, what is happening in Raspberry Pi 3 and Raspberry Pi 4, they both work the same, and there isn't much huge advantage we got from upgrading for Raspberry Pi 4, but for more stability, and we decided to, if we want in the future to add extra modules or extra devices, so it's better to work with Raspberry Pi 4. But the performance, I think, for this stage was quite the same.
Interesting.
Yeah, that's sort of surprising. There's another question here about the latency. What kind of latency did you see with like object detection and the machine learning type processes on the system?
The kind of latency, it was a couple of milliseconds. Really, it was very fast in detecting and also in sending the command to the control system in order if the wheelchair is safer to move or not. But I think the latency was about a couple of milliseconds. So it's not harmful, actually. And as we saw in the demo video, the wheelchair was passing by, and there is a passerby beside the wheelchair, and it immediately detected that there is a passerby, and the motion was stopped. So I think it was quite impressive, and it was fast. That could meet our priority for real-time detection.
Yeah, I mean that's definitely, you know, performance-wise, every millisecond counts when you're doing these real-life, you know, things, especially a safety device like this. Can you talk a little bit? I'm also I'm a big fan of the Python programming language. It's what I know best, and it's, you know, obviously there's a great Python API for OAKD. Could you talk a little bit about, you know, the code, like kind of, you know, Python libraries or whatnot that you used while creating this on the code side?
Yes, for computer vision, we used the supported Depth AI module that is come to the show, and we used the examples that is supported by Depth AI examples, and we used mobile net SSD OpenVINO model that is supported, and we made just a little modification for the detected parameters like the X, Y, and Z 3D coordinates, and we wanted to convert those coordinates into an angle and distance, and the reference would be the camera, or in our case the wheelchair, and the camera fixed on the wheelchair to make that wheelchair is a reference, and according to the place of the detected object in terms of the angle and the distance, we could use it in converting it to longitude and latitude using our made equations. So that's it. We used the supported modules that came with Depth AI.
Yeah,
But for the rest of the system, did you use Python or did you use C++?
Yes, for the PCI system, in terms of processing the model and processing the data, we used Python only. And for the controlling of the wheelchair and the embedded system, we use the C++ language because it's faster, of course, with the hardware. But for the processing and the classification models, Python has a lot of support, of course, and we used Python, and we find it's good in terms of the accuracy and the time of processing as well.
Right, and the development time also.
Yes, of course, the development time is the main reason.
Yes, Python's great. Everybody loves Python. There's another question here about training these classifiers for the brain-computer interface. Like, how varied are the signals between different people's brains for trying to do the same task? Like, were you surprised by how similar they were, or how different they were? Like, what's the range there?
And also, was there any personalization required for every person, or you could train once and that is it?
Okay. Actually, we found out that for each human, there is a huge differences between each signal. And that depends on the power of the signals that is produced by each one. We are different, and each biological operations and process in our body differs. So we found out that the pattern of each signal for the one direction, so as example, the right direction, we detected that the pattern is similar, but the range of the millivolts that produced by each individual differs according to many stuff. So we collected the data on several sessions, and for each session, the individual signals differs for each session. So I guess there is a huge difference between us and huge difference in our current mood or our health condition, but the shape of the patterns is still the same for each direction. So we could filter and doing our signal processing in order to detect those patterns and distinguish between them.
So you did not ultimately, you did not have to train a person's specific model. The same model that you trained worked for everybody. Is that right?
Yes.
That's great.
Yeah, it's really interesting. I've always been fascinated by those the BCI kind of helmets. We used to see them at CES every single year when I was with Occipital, and you'd always see them, but like nobody really used them for anything. But they were always there and like had these big booths, and they were cool. But it's really interesting to see these finally being mature enough to be used in a successful project like this.
I have another question about this data collection. So ideally, so the signal, if you think about moving right, for example, right, versus when you move right using a joystick, for example, right? So the two things, do they produce, let's say you put a helmet on me, right, the headset on me, and you just ask me to think about moving right, that will be one signal. And the other thing is that I sit on this wheelchair and I'm actually just moving I'm not consciously thinking about it, but I'm moving the joystick. Are
Yes.
those signals, maybe the brain also generates a signal at that time when I'm moving the joystick right. Are those two signals the same or are they different?
No, it actually differs because each part of the brain is responsible for a specific task. So if you move your hand or move the joystick to the right, it will generate a signal in movement, the cortex that is responsible for movement, the organs. But imagining movement, there is a different part in the brain that is responsible for those kind of generation of signals when we imagine movement. So they aren't the same. And also we take that into consideration that the movement cortex and the premotor cortex and premotor cortex are sequentially in front of each other in the brain parts. So we try to reduce the influence of the motor cortex on the premotor cortex by detecting the artifacts that is produced by kind of movement for the body. If any volunteer moved his hand or his legs, so we try to reduce and eliminate these artifacts from the signals. By using the 8 electrodes, we distribute them 4 in the motor cortex and 4 in the premotor cortex that is responsible for imagining movement. The first 4 electrodes that put on motor cortex used for filtering and eliminating those data.
Interesting.
So yeah.
Interesting, because the reason I asked, and unfortunately it did not work out, is that if you have a mechanism where a person using something normally creates data for you automatically, that's beautiful, right? For example, if this actually worked, right, if it was the same whether you move the joystick or whether you imagine, then you can simply put this headset on regular people using a wheelchair, and they would generate infinite data. They would generate a lot of data for you, and that happens in the auto industry quite a bit, where, because you have information about brakes, when people hit the brake. So you can synchronize it with the camera data, and it is automatically annotated in some sense that, oh, all the important, because you could have hours and hours of data, but because you also have data from accelerate, the gas pedal as well as from the brakes, you can know, which pieces are important to look at. So the data gets automatically generated, automatically labeled. So it did not happen this in this instance, but as a general problem, we should look for opportunities where data annotation becomes free.
Yes, I guess it would be a very, very useful thing, because anyone wanted to make the research right now in some particular areas like we have done. We didn't find quite a lot of data about the EEG signals using the similar sensors that we used. So we tried to make our own dataset and train it, but it would be very different experience if we tried or if we found a dataset that is used the same kind of data and the same kind of headsets. It would be a different experience, of course.
Right.
For that, we've got a question here about calibration. I feel like every week there's a question about calibration. This one particularly is asking about how did you fuse the data between the three OAK-Ds? What, there some custom calibration you had to do in order to get them to, be able to talk to each other, or were they just kind of siloed from each other?
Okay, my friend Abdurrahman will answer this question.
Okay. We have safety issue. Each sensor, IMU sensor and ultrasonic sensor send a CAM message that we have a specific ID for each message, IMU and ultrasonic, and we make a simple algorithm that check the condition ranges for every for IMU orientation and distance from OAK-D cameras and ultrasonic. We have a priority in
and that's also implemented on our spree cameras. Is that right?
Yes. We implement all that on our microcomputer board that takes all this information and check on simply on ranges for every reading, then make a decision according to the readings from each sensor. And if any one of them is unstable, we immediately stop the wheelchair motors.
Okay, so from what I'm hearing is that you did not require very strong calibration. You did not need to know exact calibration between the cameras, but you checked whether the camera it's completely off, right? I mean, if the IMU shows that it has turned upside down, then obviously you should ignore that camera, maybe stop the wheelchair for safety reasons. But you do not need any very strong calibration between the three cameras.
No, we don't need to do that.
That makes sense.
I think we're running up on time. You want to take us home, Satya?
Yeah, thank you so much for presenting. It was great to see. It was, these are the things that are completely outside my expertise. So it was great to learn about EEG signals and headsets, etc. Great submission, and congratulations on winning the third prize in the grand prize case and winning the top prize in your region. It is really, really impressive what you guys have done in a short period of time.
Thank you, Satya. Thank you for this kind work.
Yeah, so that brings us to the end of this weekly webinar. Just, I need to have a few more announcements. Black Friday is coming, and we will have a sale on our courses. OAK-D Lite, that campaign is still going on Indiegogo. So if you are interested in OAK-D Lite, please go and check it out. And we will be back with our webinar again next Thursday. Thank you, Phil.
And also, don't forget, OpenCV AI contest is currently still open. It's accepting submissions. I just posted the link in the chat here for everybody. Next week will be a tutorial episode, so join us here once again, Thursday, 9 a.m., same bat time, same bat channel.
That's great. Thanks. Bye.
Thank you.
No.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by Microsoft Azure and Intel, sponsors of the world's largest spatial AI competition, OpenCV AI Competition 2021. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.